where we left off.
Like I had an interview.
Okay. So, all right. So remember that we defined the kernel density estimator. So it's the average scale kernel function. And the first thing we wanted to do is work out the bias. So we just took the expected value, did a change in variables in the Taylor series, and what did we see? That the mean of this thing minus the true density was, we showed it was h squared over 2 times the second derivative, and there was some constant there. And we didn't continue the Taylor series, but remember the first term disappeared because of the symmetry of the kernel. That's true for all the odd ones. The third term would disappear, the fifth term would disappear, same argument. So the next term of the series would be order h to the fourth, which is clearly when h is going to 0, that's much smaller than this. So that's why if this n gets bigger, we can ignore this term and concentrate on this term. But what we're interested in, remember, was the, I'll call it integrated mean squared error. This was our risk function. Which remember, that was the integral of the bias squared plus the variance. Well, we've just figured out the bias squared at a particular x. So therefore, the integral, let's write one more line here. This is approximately b squared over 2. Actually, let's just all call this all a constant now. So what we get is that this is, actually no, let's leave that there. Leave that. This first term, the integral of the bias, therefore, is h to the fourth over 4, some constant integral. This is, remember we started off talking about we need some restriction on the smoothness of p, and I said one way to do it is through looking at the integral of the second derivative. Now you can see it kind of comes up naturally here for doing this calculation. In fact, this is again some number, so let's call all of this a constant. I'm just going to keep, I'm going to use the convention here that whenever I write c, I mean some constant. It could change, so the c here and the c here is a bit different now because this c includes this and the 4 and so on. So c is like a generic constant that can change from expression to expression. And so now we have a squared bias. The variance can be done in exactly the same way. It's done in the notes, but basically remember how we derived the bias is we noticed that I could write this as an average. Well, yi is just everything inside that sum. And so the variance of this, the variance of a sum is, what's the variance of x bar? It's the variance of xi over n. Right? It's the variance of one of them over n. Now, you do exactly the same thing. I'm not going to go through the same calculation because it's almost the same. So you write out, what did we do? We took the definition of expected value as an integral. Well, the expected variance is another integral. You do a change of variables in Taylor series. I think I have the steps in here, but they're so similar to what we just did for the bias. I'm just going to tell you the answer. It ends up being p of x over n times h times some other constant. So that's a very similar calculation. And so now we can combine them, and we get that the risk, or the mean squared error. So some people, we call it the risk. Some people call it the integrated mean squared error, whatever you want to call it. It's the bias squared plus the variance plus smaller order terms. And that was the expression I gave you right when we started. And remember, what we saw was that the optimal h, if I minimize that, that was of the order n to the 1/5. Just by taking the derivative and set it equal to 0. And then we said that the risk, if I plug in the optimal bandwidth, was something like n to the 4. So that's how I got that. I stated that right at the beginning, and it was just by doing these calculations. So now we know quite a bit about the risk of the total density estimator. Now, does this actually tell us how to pick the bandwidth of practice? It does not. Why? Because I keep writing constant here. That constant contains a lot of stuff. Among all the stuff that's contained in the constant is this thing. Constant depends on p double prime of x. We don't know p double prime of x. So this expression that we derived is purely for theoretical reasons. This was to help us understand the theoretical properties of the current density estimator. And it tells us qualitative information about the optimal bandwidth. It should go down to 0 at a certain rate and so on. But in practice, we don't use that to select the bandwidth. So how do we select it? Well, in practice, there are a variety of methods to select the bandwidth, and they're based on things like cross-validation and so on. So this is stuff we talked about in 702. Since this is not a course on density estimation, I'm not going to go into details about that. But I do want you to know that the practical methods for selecting the bandwidth are a bit different than what we've just done here, which are just studying what's going on theoretically. Okay, so what we just did is just a theoretical calculation. It's important, but it doesn't answer the question about picking the bandwidth. But there are good ways to pick the bandwidth in practice. Basically, what they come down to is we have this risk function, and the way that we think about it is the risk function is not really known. It depends somehow on the unknown density. In fact, you can see it depends on p double prime. But if we think of the risk function itself as a parameter, we can estimate that parameter. And what we get is an estimated risk. And what we do is we think of that estimated risk, and we say, how do we minimize that over the bandwidth? And that's how we end up choosing the bandwidth in practice. So, in R, for example, if you don't tell it the bandwidth, it'll do that for you by default. And perhaps I would assume MATLAB does something similar, I don't know. So I wanted to give you here a little flavor of a non-parametric problem. We're not going to study this in great detail. I did want to tell you, though, that if I did this in d dimensions, so now, in principle, not much changes. The kernel density estimator is basically the same, except that the 1 over h has to become 1 over h to the d. And the k you can just think of now as a multivariate normal. Or some other, you have to think of it as a function. Let's suppose the data are two-dimensional. Now, instead of being a function like you draw on the blackboard, it's a function, over R2. So just the typical example would be, think of it as a spherical multivariate normal would be an example. And so, once you choose a kernel that lives in this high-dimensional space, it's just the same formula. But what changes in the analysis is that the integrated meter or risk ends up being of the form. And again, this is something we study in some detail in 702. The bias term is the same. The bias term is dimension independent. Where the curse of dimensionality shows up is in the variance. The variance, that makes the variance when h is small much bigger. Estimator gets much, much more variable in higher dimensions. In particular, the final risk at the optimal bandwidth turns out to be of order 1 over n to the 4 over 4 plus d. So notice that when d is 1, it's 4/5, which is what I derived. But you can see that when d gets big, because it's in the exponent, this risk gets very, very poor very quickly. That's the curse of dimensionality. There's two curses of dimensionality. The computations are much harder in high dimensions, just take longer. But the accuracy of the estimator, without further assumptions at least, also gets much worse. Okay, so I'm just kind of previewing stuff that's in 702. Really for this class, just knowing that basic one-dimensional result is all we really need to know for this class. So So we've now seen two problems, how to estimate a CDF, how to estimate a density. I'm about to go on to the third problem. Are there any questions about the estimating the density? Yes?
What, I can't quite see what you wrote on, O of 1 over,
Oh, this, let me write it bigger for you.
thank you.
Try to find a way to make this readable. Okay, like this. Actually, I'll just do it like this.
Thank you.
Any other questions? Okay, so let's turn to our third non-parametric problem, which is estimating a statistical functional. What does that mean? What that means is we have a probability distribution or a CDF, whatever, and I want to estimate some quantity that depends on P. So the way to think about this is the set of distributions. And suppose I assign to every distribution a real number. So that's our, call this theta. So what do I mean by that? Well, an example would be T of P is the mean. So that would be like, what that's really doing is you can think about it like, it's like a computer program that you stick in a distribution and it outputs a single number, the mean of that distribution. So it's a mapping, right? It maps every distribution to a real number. And so we call that a statistical functional. And the goal here is to try to non-parametrically estimate this. Now there's a little bit of confusion in the terminology. A lot of people will now refer to this as a parameter, meaning something that needs to be estimated. But we're not talking about a parametric model. We're not saying that this parameter specifies the distribution. So this is a different use of the word parameter. It's just another word. I mean, the formal word would be statistical functional. That's a mouthful, so people would say parameter. But here, parametering, it doesn't mean we're in a parametric model. We're not going to make parametric assumptions about the distribution. We're going to be doing it non-parametrically, but the quantity that we're estimating will typically be some real number. So we'll often call that a parameter. So it's a different use of the word parameter. It's an unknown quantity that we want to estimate. So how are we going to do this in general? Well, before I do that, there's one piece of notation that's going to be extremely helpful for this section, which is, and this is right, I think I have this, yeah, right on page 5, which is, I want to be able to write the integral of a function, like I just did, with respect to the distribution, but I'm going to often write it in what looks like a weird way. I could write it like this. So here's a given function g, and I want to talk about the mean of g. So I'm going to sometimes write it like this. I'll write g of x, and this is the CDF. Or I might write it like this. This is just the probability distribution. Probability. What does this notation mean? Well, if you've had real analysis, actually, you know it has a technical meaning. But if you haven't, that's okay. I'm just going to define it the following way. What I mean is, this is just shorthand, which is, if x is a discrete random variable, all I mean is the sum. I mean, it's g of xj times the probability function. And that's, how do we compute the mean of a random variable? Well, you would just take g of x times the probability function, right? But if it's got a density, we interpret it to be g of x times the density function. the x. Okay? But instead of having to keep writing, this is what I mean for the discrete case, and this is what I mean for the continuous case, I'm going to use this unified notation. It just simplifies things. But just remember, if I write this expression, just think in your head. If it's discrete, I'm just writing the mean the usual way. If it's continuous, I'm just writing it the usual way. Just okay, so it's really just, for our purposes, it's really just a shortcut notation for that. Is that clear? Any questions about that? Because I'm going to use this repeatedly now. And I might put it in terms of the CDF or the probability. It doesn't matter. It all means the same. Keep that in mind because this is going to come up right again. All right. The next thing I need to remind you about is the empirical distribution. Well, we talked about the empirical CDF in one dimension, but in general, there's always an empirical distribution. Let me explain what I mean. Which is, it could now be that the data aren't in one dimension, it could be 2 dimensions, 3 dimensions, but I can always define an empirical distribution much like the empirical CDF, which is just to put probability mass 1 over n at each data point. So, sometimes, remember in one dimension, I defined the CDF, the empirical CDF, do this. That's equivalent again to just saying I'm going to put mass 1 over n at each observed data point. But if the data were here, say in 2 dimensions, and I have data, I can still define a probability distribution which puts mass 1 over n at each data point. So I'm going to denote that in general by a piece of that. This is the empirical distribution. Empirical. And how can I define that in general? Well, all I mean is that the probability that I'm assigning to any set, okay, is just going to be the proportion of points in A. So this is just 1 over n times the indicator function. Right, this is just the proportion of points in any A. That defines a probability distribution. And it's the, you can think of that as the estimator for the true distribution. That's a non-parametric estimator for the true distribution. Of course, P of A, this would be the true probability. And we know that, for example, if I just focus on one event, we know this is close to this by things equal. What I want you to think about this thing now as a whole probability, it really is a probability distribution over the whole space. You can compute the probability of any event. And so we should think of this empirical distribution as some sort of estimate of the true distribution. And sometimes, so why do I sometimes write CDF and the empirical CDF, or the distribution and the empirical distribution? It's just really, maybe I should just be consistent with one or the other, but I tend to go back and forth. But they're really the same thing, right? If you know a probability distribution, then you know it's CDF. And remember, a CDF tells you everything you need to know about a probability distribution. So sometimes we talk about the probability, which is, let's go back to the real line. This is like telling me the probability of every event on the real line. Sometimes we talk about the CDF, which is only telling me the probability of x being less than or equal to x. But you can always go back and forth. This determines this, and there's a theorem that says once you know this, you actually already know this. So sometimes I'm going to write P's, sometimes I'll write F's. There's no distinction, is what I'm saying. I'm just sort of being a bit sloppy, perhaps, by not picking one or the other. But don't worry if I write sometimes F or sometimes P, whatever you prefer.
What would be the difference between estimating the empirical CDF and the empirical distribution?
There's no difference. This is an estimator of this. But the only theorems I gave you about how close they are were in one dimension, and in terms of the CDF.
And there's what order that CDF is impossible to define?
CDF in 2 dimensions is still well defined because it's about rectangles of this form. It's the probability that x1 is less than something and x2 is less than something. The only difference between so the CDF is perfectly well defined in high dimensions. The only difference between the CDF and the probability distribution is this is telling you the probability of every event. This is telling you the probability of some subset of the events. Actually, a VC subset of the events. But they're the same in the sense that this determines this, and though it's not obvious, once you know this, you can actually figure out this. So whether I talk about CDFs or probability distributions, it's a matter of convenience or taste, and there's no real difference. I'm just saying this because I know in the notes I flopped back and forth. I know between sometimes writing P and sometimes writing F. If you prefer, I should just make them all P's or all F's or something like that, which is probably what I should do. All right, anyway. Let's get back to the problem at hand, which is I want to estimate this parameter, as we're calling it, T of P. Let's think of some more examples. So I gave you one example of a functional, statistical functional, which would be T of P is the mean of X, which now I could write like this, right? Another functional would be the variance. What is the variance? You can think of that as a functional, that is a function of the distribution. Why? Because, well, I can write that as the expected value of x squared minus the expected value of all x squared, but I can write that as x squared dt minus the mean squared. It's a functional in the sense that, in principle, you could always write a computer program that if I gave you the P, you could now compute this and get the number out. It maps a distribution or a probability distribution to a number. The median. Let's think of, now this is where it's more convenient to think in terms of the CDF, because the median, and let's say the distribution is increasing for simplicity, then what's the median? Well, I know it's the point that has half the probability to the left and half the probability to the right. So there's half here and half here. But what does that mean? That means the median is also a statistical functional. It's really just at the inverse of a half.
If the CDF is not one-to-one, then the inverse is X.
Then we have to define the median slightly differently. It's still well defined, but let's just do the one-to-one monotone just to keep it simple. But you're right, if it's not, if it feels like a flat spot, then you would take the inf of all, or the sup of all values where it's half. But we'll do the monotone. So lots of things we think about, in fact, pretty much everything you can think about can really be thought of as a function of the distribution. Any of you done PCA yet? So the PCA, for those who know PCA, what is it? You're finding the covariance matrix of the distribution, then you're finding its spectral decomposition into eigenvalues and eigenvectors. That spectral decomposition is a pretty complicated thing. It's just some functional P. Everything you can think about is really just a functional P. Not everything, but everything that we care about for statistical purposes. So this is like a different way of thinking about statistics, which is just you think about what you want to estimate and you think of it as a function of the distribution. And once you do that, it gives us a different way to think about how to estimate a parameter non-parametric. Because we know that the empirical distribution, again, can be thought of as some sort of estimate. This is an estimate of the true distribution. So there's a very natural way to estimate functional, which is called the plug-in estimator. Which is, we define theta hat to be TPM. And the true parameter value is you apply your function, like say the mean, P. The plug-in estimator is you apply the same function to the empirical. Because if this is an estimate of this, then you can think of this as an estimate of Very simple idea. Now we're actually going into treacherous territory, I have to tell you, because the whole study of when are plug-in estimators good estimators is a very complicated subject, and a lot of times they're not good estimators. And then there's a whole theory about how to correct a plug-in estimator when it's not a good estimator, and so it's kind of a complicated subject. We're certainly not going to cover that entire subject here. So in all the examples we're going to consider, it's going to turn out the plug-in estimator just turns out to be a pretty good estimator. But I don't want to leave you with the impression that that's always true. There are cases where the plug-in estimator is not a very good estimator. And if it's not, there are methods to say, okay, it's typically what can go wrong, I'll tell you, is that often it can have a lot of bias. And a little bit of bias is okay, but often it can be very biased. And then there are methods to try to estimate the bias and subtract off the bias. So it's quite a complicated stuff. This is called, in statistics we call it semi-parametric inference. The whole branch of statistics devoted to this. So I'm going to keep us focused on pretty simple functionals where we don't run into any problems. But I'm just keeping in the back of your mind that I'm not suggesting this always works perfectly. But there are lots of cases where this is going to work, and let's do a few examples, and then see how once we have the estimator, it turns out doing everything we want, which is getting the best confidence, and it turns out often to be quite simple. So let's start with the mean. So what is the functional? So let's say the mean. I want to estimate the mean, but I want to do it non-parametric, without assuming parametric laws of the true distribution. So I say, well, theta is T of P. Okay, now comes the key step. Watch this. So my plug-in estimator is T of Pn. So all that means is I take the definition, and wherever I saw the true distribution, I put in the estimator. Okay, that sounds easy. So I'm just going to say this is X. Yeah. Now, what does this mean? Now we have to go back to when I originally started talking about my notation, right? I said, that means, did I keep that somewhere, or is that already gone? That means, well, it's gone. But remember what it meant. It meant the integral of x times the density if it was continuous, and it meant the sum if it was discrete. This is a discrete distribution. In fact, let's rewrite another way to think about the empirical distribution, which is really helpful conceptually, is we have our data points, and when I make the empirical distribution, the way that I originally explained it, I drew a picture, you have data points and you put mass 1 over n in each data point. But it's also helpful to think about it, since it's just a discrete distribution, in terms of a table. Whenever you have a discrete distribution, you can make a table, which is what are the possible values that x can take. And so for the empirical distribution, we're only putting mass at the observed data points. So the only possible values really we're considering are the actual data points. And the probability mass, let's call it P sub j, is we're putting equal mass on each data point. 1 over n, 1 over n. So another way to think about the empirical distribution is, it's just, here's this, it's like saying the sample space from the point of view of this distribution really is finite. It's only taking n possible values. And this is the mass. It's putting mass 1 over n in each point. So it's like a table. And that helps us think about what this integral is, because this integral is interpreted, this is a discrete distribution. So it's just, what did we say was the integral of g of x, d, whatever p, when this was discrete, it was the sum, just like we learned in elementary probability, times this is every value that this can take times the probability. So what is that? It's the value times the probability. The value times the probability. Value times the probability. In other words, it's the sum of xi times 1 over n, which is x bar.
Is there a case when d p sub n is not discrete, and it's continuous, or is it always going to be discrete?
This is continuous.
No, I'm talking about.
The empirical?
Yeah.
The empirical is a discrete thing by definition. The empirical is defined to be a discrete. So that was in some sense very simple, but also, I know it's a point where people can get confused. It's kind of a little simple but slick move there. So let's make sure everybody's happy. Any questions here? We now saw something actually fairly profound, that if we're interested in the mean, the plug-in estimator as we define it is simply x bar. This is kind of interesting because we're getting the same estimator we got assuming normality. If I assumed that the data were normal and did the MLE, I got x bar as the estimator. It turns out the same estimator can come up in many different ways. And here in this interpretation, it's a non-parametric estimator. So that shows you something, that the estimator is not parametric or non-parametric. It's the model that's parametric or non-parametric. We happen to get the same estimator in a non-parametric set. You can think of x bar as the MLE under the normal, or it's the plug-in estimator from a non-parametric. In fact, what is the model here? What set of distributions can I work with for this all to be well defined?
Anything with a finite mean?
That's an excellent point. If the mean isn't even finite, then what are we even talking about? So we might say the model is a set of all distributions such that the mean is finite, so that this is well defined. But also, we usually require the second moment to be finite. Why? Because then this has a finite, we don't really want to get estimators with infinite variances, that's a bad thing. So usually when people are thinking of this as a plug-in estimator, they would say, okay, I'm only going to use this for the model in which I'm willing to assume that the first and second moments are finite. Because then we know this has variance sigma squared over n, which is some finite number. So this is a non-parametric class, like a set of all distributions such that x has a finite first and second moment. It's a pretty large class of distributions. It's not everything, but it's a very large non-parametric class. And for that class of distributions, for that non-parametric model, the plug-in estimator of the mean is simply x bar. Very simple. And we know that, by the way, what do we know about x bar? Well, it has a central limit theorem, at least under the assumption that the variance is finite. This has a central limit theorem, which is going to make doing testing and the hypothesis testing of confidence intervals very easy. In fact, in this whole plug-in world, sometimes, this is not always true, but sometimes the following is true, that if we define theta hat to be EPN, in some cases, in many cases, we will see that theta hat and minus the value over the standard error, the standard deviation of the estimator, does satisfy a central limit theorem. It's not always the case, but it's very often the case. The general theory of determining when this is true, again, is somewhat complicated. We're just going to do it on kind of an example basis. But if that's true, heck, we know what to do. We know how to do a hypothesis test. I can do a wall test. If I want to test the null hypothesis, theta is equal to theta 0 versus theta not equal to theta 0, I can use exactly the same reasoning I used in parametric models, that I can get a asymptotic size alpha test just by using by treating this as a normal. And so I would reject null if this thing, if theta hat, actually we're going to have to use a estimated standard error, but if that's bigger than the normal cutoff, it's just like the parametric case. It's just a non-parametric version of the wall test. And how about a confidence interval? Same thing. I can get an asymptotic confidence interval. I just take theta hat plus or minus and estimate the standard error. That would be my confidence interval. And we will conclude, therefore, that the coverage, the probability that theta trap C converges to 1 minus alpha. You can see why maybe we did the parametric stuff first, is it makes it very easy now to discuss these concepts because it's so similar to the parametric set. So just to give you the big picture here, what we're doing is we're going to specify a function of interest. We're going to estimate it by doing this plug-in procedure. We'll do a few more examples of that. And now, if it's asymptotically normal, we're back in a situation like the parametric thing. I can define a walled test and a walled confidence interval, and we can do everything we want now. We have a point estimator, a hypothesis test, a confidence interval. There is one catch. When I go to apply this, of course, I don't use the true standard deviation. I have to estimate that. I put an estimated standard error. How do I estimate the standard error of a plug-in estimator? Now, in some cases, you might be able to just figure it out intuitively. After all, if I ask you what's the variance of this estimator, well, without knowing anything about plug-in estimators or anything, we know that this is equal to sigma squared over n, where sigma squared is the variance of x. And we know that we can estimate that by what? By the sample standard deviation over n. So coming up with an estimate of the standard error in a particular case might be just a matter of trying to be clever and look at the variance. Maybe I can figure out the variance, figure out how to estimate it. But that's okay for simple functionals. But what if it's a pretty complicated functional? How in the world, what if I want to estimate the largest eigenvalue of the covariance matrix or something? So these functionals can be pretty complicated. How am I going to estimate the standard error of that plugin thing? And the answer is we're going to have a general method for doing it called the bootstrap that we're going to talk about on Friday. Maybe we'll start today, we'll see how it goes here today. So for the moment, let's assume we know how to get the standard error, because we're going to address that in Friday's class. Apart from that issue, then, we have a pretty simple way of doing this non-parametric estimation.
Isn't standard error also some sort of functional so why don't you do plugin?
Well, you've hit the nail on the head. That's what the bootstrap is. So the standard error is itself a functional. It depends on P. So that's just plugging in Pn there. Now there's a complication, which is it might be something not computable, but there's a way around that. That's what all the bootstrap is about. So that's what we're going to talk about on either end of today or Friday. But we'll come back to the standard error issue later. And also, once we get to the bootstrap, we'll see we don't even have to use this formula for doing the confidence interval. We can directly use this thing called the bootstrap. There's a direct way to get the confidence interval directly from the bootstrap. So we'll talk about all that. Let's, though, keep talking about these functionals, because I want to do some more examples just to make sure it's clear how you do this. So let's do the variance. So I want to estimate sigma squared, that is the variance of x. I want to do it non-parametrically. All right, so let's think about it from the functional point of view. This can be written as, let's rewrite it as 4. So that's so if we use the plug-in estimator, all I do is take the functional and replace P with Pn. So let's do that. There's our plug-in estimator. Now we can do some rewriting. Once again, this is just the discrete distribution, so we just write it as a sum. And it puts mass 1 over n at each data point, so this becomes the sum. And this is the mean squared, so this is 1 over n rearrange that a bit. How cool is that? Once again, in this case, it doesn't always come out this way. This happens to be the same as the maximum likelihood estimator in the normal model, but it's also the plug-in estimator. It's a non-parametric plug-in estimator.
Give an indication why this is happening.
Why it's agreeing with the normal in these cases? I don't have a simple explanation. It's certainly not going to be true for any other functional. So this is pretty particular for the mean and the variance. There's probably some explanation. I'm just not thinking of it right now. All right. How about quantiles? Let's take the median. The median is this. So what's the plug-in estimator? I've written this one in terms of the CDF. So what do? You take the empirical CDF. So what does that mean? Well, what's the empirical CDF? It goes like this. I'm looking where it's a half. Let's say it's there. But what does that correspond to doing? That really just corresponds to ordering the data and finding, the midpoint, where half are to the left and half are to the right. So if let's suppose there's 5 observations. Then literally finding f inverse of a half just corresponds to finding the middle observation. If there's an even number, there would actually be a whole range. That would be a case where the inverse is sort of not well defined. And so there would be, people just take any arbitrary number in between, or the smallest one, maybe it doesn't matter. But the point is that the sample median is the plug-in estimator of the true median. So there's an example where it's different from the normal. Correlation, all kinds of things that we think about. An intuitive way to think about it is, it's just the sample version of the population quantity. So you want the variance, you use the sample variance. You want the mean, you use the sample variance. It's kind of a fancy way of saying it. It's, which is a fairly obvious thing. Okay, any questions about this? Plug-in this to me.
Is the median estimator in the normal case, in the parametric case?
It's theta, because in a normal, the mean and the median are the same. And so estimating the median is the same as estimating the mean, and so it's MLE. But yeah, whereas here it's the sample median. So I think you can see there's a whole wide range of problems you can apply this to. Now, there is a warning, which is, I've been picking pretty simple functionals, and it is true sometimes in complicated functionals, you can get a poor estimator. So, that's a whole other topic, and we're not going to go into that. So I just want you to be aware that you shouldn't just assume it's always going to give you a good estimator. But the big issue is, how do we get the standard error and hence the confidence interval? The principle is pretty simple, and the estimator is very simple, very intuitive. And I want to leave that, then go on to the bootstrap. So any questions then about plug-in estimation? We'll do some more of this when we get to the bootstrap. Just to back up a bit. So now we've seen 3 problems. Estimating the CDF. Now you can see why I wanted to estimate the CDF first, because it really plays a role in the plug-in estimate. So we know how to estimate a CDF, or more generally a probability distribution with the empirical distribution. We know how to estimate a density. We know how to estimate a statistical functional or non-parametrically defined parameter. And And I'm ready to, so there's another optional section, this is section 4, you can put a star there. It's a very cool thing, but I don't think I'm going to go into it, which is, suppose you wanted a confidence interval for the median. There's a very, very clever way to get a very simple, completely non-parametric confidence interval for the median. And it turns out, I'll just leave it there as optional reading, but what it comes down to is you order the data, and then the middle point, the sample median, is your point estimator. But it turns out if you choose one of the order statistics over here and one of the order statistics over here, and then I'll show you exactly which one to pick. Those two numbers give you a confidence interval, and it's a real, it has the property that the median, let's call it M, is in that confidence interval, is always greater than 95%, without any assumptions on the distribution. And there's no asymptotic approximations involved. So it's an example, I wanted to show an example of something where we get a completely non-parametric confidence interval without using asymptotic normality or approximations or anything like that. It just uses some clever calculations with the order statistics. So just put a star next to that section. It's optional reading, although you probably should look at it just so you've seen it. And I just like that example because it's just a nice clean example of where you can do a completely non-parametric analysis. Just, if you ever want to estimate a median, there's no reason to assume any sort of parametric model because we know how to get a point estimator and we know how to get an exact 95% confidence interval without any assumptions at all. So I wanted to have that in there so you could see it. But of course, the median's a pretty special and simple quantity, and we can't always get these such simple confidence intervals. So what I want to start talking about now is what I think is one of the coolest things in statistics, which is very popular in statistics. Is that a question?
Yeah.
Yeah.
I guess less cool, so you had, when we estimated the CDF, right, the empirical CDF, like theoretically, sure, you can go from the CDF to the PDF, but the empirical CDF that we get is like very, stepwise, right? So how do you kind of estimate the PDF in real life?
Kernel density estimate.
Okay.
That's exactly why we did that. You're absolutely right. Going directly from the CDF to the PDF will not work. The densities are very, some objects require, so a plug-in estimator of the density will fail. That's an example actually where the plug-in estimator fails. And we had to do kernel smoothing. Yeah, actually, that's a good example of where plug-in principle doesn't work. Good question. So, just to give you, we'll just start the bootstrap and then we'll continue on by it. So, as I say, it's one of the coolest things in statistics. And here's one of the interesting things. It's used all the time in statistics, but it's not used so much in machine learning. So there's a lot of things in machine learning that have migrated over to statistics. And there's a lot of things in statistics that have migrated over into machine learning. But the bootstrap, for some reason, I think I know why, but we can talk about that later. It's not, I don't think, permeated the ML literature so much. I've seen it used here and there. So it's a good thing to know about because then you'll know something most of your other colleagues don't. But it's a very, very cool thing. And what it is a very, very general method for getting standard errors and confidence intervals in a very non-parametric way. And it requires absolutely no calculus, no computing information matrices, no scalar functions. It's completely automated. It's all done by computation. And so it's a really, really interesting thing. It was invented by Brad Efron in 1973. He was a statistician at Stanford. And really important part of statistics. At the same time, the thing about automatic is once you see how this works, you're going to immediately see you can code this up. 4 lines of code for any problem you're working on. That's the good news. Very easy to code. The bad news is it's very easy to code because that means everybody applies it everywhere, even in places where it doesn't work. Because like any procedure in machine learning or statistics, it requires certain assumptions to go wrong. You make any procedure, and there's going to be cases when it works and cases when it fails. And the bootstrap requires some assumptions. It's not magic. And so one of the things I want to show you on Friday is that yes, it's an amazing thing, and yes, it works for a large class of problems, but it doesn't always work. There are certain assumptions that are going to make it work. So it can be dangerous that I see people applying the bootstrap everywhere, even in places where it doesn't work. So we'll talk about the bootstrap from start to finish on Friday. How about the test next week? I'm surprised no one's asking about that. See, now the questions start. So the test is on Friday. Why do I have so many tests? Because robustness. If you only have one test and you screw it up, you totally screwed up the grade. So if you have lots of tests, every one test is a very small influence, right? So it's much better to have many tests. And what the next test on Friday, a week from Friday, is only going to cover hypothesis testing and confidence intervals. Okay, I'm just going to focus it on those two topics. Yes, I will post a practice test, and Wednesday, as usual, will be a question and answer class to do any review. All right.